In this problem, we have a challenge. Imagine you have a polynomial with integer coefficients. For example, x squared minus 5x plus 11. We're told that this polynomial spits out the value 7 for 4 different integer inputs. The question is, can that same polynomial ever spit out this value 14 for any integer input? Well, it seems like it could, right? However, let's prove that it's actually impossible. First, we can set up this problem as a new polynomial. The key to this problem is to focus on the roots of the polynomial. The statement px equals to 7 is not about roots because the right side is not 0. So let's make it about roots. We can let the 4 distinct integers where px equals to 7 be a, b, c, and d. Basically, we'll have pa equals to pb equal to pc equal to pd equals to 7. Now, let's define a new polynomial q of x as q of x equal to p of x minus 7. Now, since p of x has integer coefficients, q of x must also have integer coefficients. So what are the roots of q of x? They are the values of x for which q of x equal to 0. So, indeed, we'll have q of a will equal to p of a minus 7 equals to 7 minus 7 equals to 0. Now, the pattern repeats for a, b, c, and d. So we know that a, b, c, and d will be the 4 distinct integer roots of the polynomial q of x. Now the next key step will be to apply the factor theorem. The factor theorem tells us that if r is a root of a polynomial, then x minus r must be a factor of the polynomial. Since a, b, c, and d are all roots of q of x, then x minus a, x minus b, x minus c, and x minus d must all be factors of q of x. Now, because all the q coefficients are integers, we can write q of x in the following form. Q of x would equal to x minus a, x minus b, x minus c, x minus d times r of x, where we let r of x be another polynomial that must also have integer coefficients. This is a critical property of polynomials with integer coefficients. Now let's address the main question. We want to prove that p of x can never be 14 for any integer x. So let's assume the opposite and see if it leads to a contradiction. This method is called proof by contradiction. So assume that there exists some integer, let's call it k, such that p of k equals to 14. So we assume p of k equal to 14. Now, if p of k equals to 14, then we have q of k equals to p of k minus 7, which is 14 minus 7, equal to 7. But we also know that the factor form of q of x, we can plug k into that. So we have q of k would equal to k minus a, k minus b, k minus c, k minus d times r of k. Now, combining these two will give us our central equation, which is k minus a times k minus b times k minus c times k minus d times r of k equals to 7. Now, let's look closely at the terms in this product. Since a, b, c, and d are all integers, the terms k minus a, k minus b, k minus c, and k minus d are all integers. Since a, b, c, and d are distinct, these 4 integer factors must also be distinct. For example, if k minus a equals to k minus b, then a equals to b, which is false. Now, since r of x has integer coefficients, r of k must also be an integer. So, we have written the number 7 as a product of at least 4 distinct integers. Now, the factors of 7 we know are 1, -1, 7, -7. That's it, there are only 4 of them. Can we find 4 distinct integers from this set that multiply to 7? Now, the only way to use all 4 is to multiply them together. And we know that 1 times -1 times 7 times -7 equals to 49. The product here is 49, not 7. If you try to use any 3 of them, like 1 times -1 times 7, which is -7, it's also not 7. What if R of k helps? If the 4 factors are, say, 1, -1, 7, -7, the product is 49. Now we will need R of k to be 7 over 49. However, this is not integer, so we can't use it. So no matter how you look at it, it's impossible to write 7 as a product of 4 distinct integers. So this is our contradiction. Our assumption that there exists an k for which p of k equals to 14 must be false. So we have arrived at our conclusion that p of x is not equal to 14, no matter what input we have as x. And that is how you prove this problem.